NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto is a faraway and confounding planet, which was once a member of our nearby planetary family. However, recent statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this chilly world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such an immense event? Are we witnessing a rare cosmic anomaly, or is there more to this impending celestial encounter? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet largely due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's orbit dangerously intersects with Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it has not even completed one full revolution. Yet the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, measured at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of space mechanics. The three-body problem in space, determining how three objects like Pluto, Neptune, and the Sun move and interact with each other's gravity, is key. It's like predicting where they will go based on where they start and how they pull on each other. In Pluto's case, this problem reveals how its path, Neptune's path, and the Sun's gravity all work together in a complex way. Terms like azimuthal libration and vertical libration, along with the VZK oscillation, are critical pieces of this puzzle. According to astrophysicists, azimuthal libration keeps all planets in their orbits. For Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from overlapping. Vertical libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated well above their orbital plane, providing an extra layer of protection from potential collisions. Another key aspect of this situation is the VZK oscillation, named after three researchers, von Zippel and two others, who studied how objects move in space. This concept explains how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. For Pluto, the VZK oscillation helps us understand why its orbit around the Sun is so unusual. Even though Pluto's path appears chaotic, this oscillation helps maintain its motion smoothly for millennia. The VZK oscillation shows that, even when things in space seem wild and random, certain patterns and rules maintain order. These factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. The three-body problem further illustrates how these forces change based on how these celestial bodies pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant worlds and stars. Numerical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is inherently chaotic, with minor deviations in initial conditions leading to massive differences over millennia. However, these peculiar properties of Pluto's orbit have been found to maintain stability over extraordinarily long timescales, effectively managing the chaos. Recent virtual simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where, for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's path consistent. But Neptune isn't alone in this effort. Jupiter's gravity also plays a significant role in protecting Pluto's orbit. In fact, Jupiter's gravity alone is strong enough to ensure Pluto remains on a stable path for a very long time, even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to keep Pluto in check. Despite the stability offered by this intricate gravitational dance, recent studies suggest that even a slight disturbance in this delicate balance could have catastrophic consequences. For instance, if an external celestial object, a rogue asteroid or a passing star, were to perturb the gravitational equilibrium of the solar system, it could set off a chain reaction. Such a disruption might slightly alter Neptune's orbit, which could, in turn, destabilize Pluto's precarious path. Astrophysicists caution that while the probability of a collision is extremely low due to the mechanisms of resonance and libration, the chaotic nature of Pluto's orbit over billions of years makes such events theoretically possible. If such a collision were to occur, it could unleash a massive release of energy, potentially sending debris into the inner solar system. This debris could pose risks to planets like Earth, raising questions about the long-term safety of our cosmic neighborhood. The theoretical possibility of a Pluto-Neptune collision also opens up intriguing questions about the formation and evolution of the solar system. Was Pluto always in its current orbit, or was it captured into this complex resonance with Neptune over time? Could similar orbital dynamics be occurring in exoplanetary systems around other stars? Researchers are now leveraging advanced computational models to simulate scenarios involving perturbations in Pluto's orbit. These simulations aim to explore not only the risks of a collision but also the potential changes to the orbits of other celestial bodies. The insights gained could deepen our understanding of gravitational interactions and help us identify other systems in the universe where such complex orbital dances might be occurring. For now, Pluto remains a mysterious yet stable member of our solar system's extended family. Its eccentric orbit, coupled with the protective gravitational forces of Neptune, Jupiter, and Saturn, ensures its continued journey around the Sun. However, the story of Pluto and its interaction with Neptune serves as a reminder of the dynamic and ever-changing nature of our cosmic environment. As humanity continues to explore the outer reaches of the solar system, perhaps through future missions to Pluto and beyond, we may uncover new secrets about this enigmatic dwarf planet. Until then, Pluto's tale remains one of resilience, chaos, and balance, a testament to the wonders of the universe and the forces that govern it. Keeps on moving securely in space without running into inconvenience. These idiosyncrasies are pivotal in the more extensive setting of the universe, keeping the control and consistency of divine bodies' developments. Without these components, our nearby planet group would be a substantially more tumultuous and eccentric spot. Bodies like Pluto might actually collide with others or be catapulted from their steady circles, prompting an impact on other divine bodies. For Pluto particularly, With discussions about it potentially crashing into Neptune later on, understanding its circle is vital. It gives us a more clear image of the planetary group's dynamic nature. The situation of Pluto delineates how even the most apparently unsteady circles can achieve a condition of equilibrium through the mind-boggling transaction of gravitational forces and orbital mechanics. It likewise shows the significance of persistent perception and investigation of these peculiarities to better understand our place in the universe. Exploring the profundities of space often drives us to face the whimsical nature of celestial bodies, and Pluto's orbit is an ideal portrayal of this unpredictability. The concept of orbital turmoil, which refers to the delicate dependence of a celestial body's path on its initial conditions, is strikingly demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can drastically change its long-term orbit. Using programmatic simulations has been incredibly helpful for scientists to understand how Pluto moves in space. These simulations utilize advanced mathematics to model how Pluto and other space objects like Neptune interact. By tweaking minute details in the simulations, astronomers can see how even small changes can have a significant impact on where Pluto ends up. In the late 1980s, these simulations revealed something truly fascinating about Pluto's orbit. Despite having stabilizing factors like mean motion resonance and orbital inclination, its path can still be wild and unpredictable. Even a small difference in where Pluto starts or how fast it moves can lead to drastically different outcomes over millions of years. Yet, even with this chaos, Pluto's orbit remains stable for billions of years. This means Pluto's journey around the Sun has some inherent order, despite appearing chaotic at first glance. Predicting such long-term events, especially when they involve erratic orbits like Pluto's, presents immense challenges. The inherent unpredictability of these systems means long-term forecasts are often filled with uncertainties. While mathematical simulations provide a powerful means to understand and predict the behavior of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different results, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made great strides in understanding space, the case of Pluto serves as a reminder of the limitations in our knowledge of the cosmos. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are significant astrophysicists only now raising concerns about a possible collision between Pluto and Neptune? Despite the complex forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. His position on Pluto's reclassification stems from the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but as a significant adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much more there is to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space. Focusing on the often unpredictable forces that shape our universe, Kaku is known for his ability to connect complex scientific concepts with futuristic visions, making him a significant voice in discussions about celestial mechanics and their broader implications for humanity. Kaku's views on Pluto and its orbit underscore the need for continuous observation and advanced modeling to predict and understand potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not only for academic interest but also for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a hypothetical scenario but a reminder of the dynamic and often chaotic nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from their impact on our understanding of the solar system to the possible need for future space interventions. Kaku's perspective highlights the importance of being prepared for the unexpected in space. His work suggests that the more we understand the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's perspectives converge on the idea that space is a realm of endless discovery, and that our current understanding, while vast, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding celestial mechanics as they are now but also speculating on how they might change in the future. The potential collision between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for rigorous scientific inquiry, cutting-edge technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action, for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that for the foreseeable future, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational effects acting on them. Therefore, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they might pose. While the possibility of a Pluto-Neptune collision remains largely hypothetical and considered improbable with our current understanding, it highlights the importance of ongoing exploration and observation in space science. Advances in technology, including improved telescopes and simulations, will help astronomers refine their models and predictions, ensuring we stay abreast of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for continuous research and an adaptable understanding of our universe. The potential collision scenario, while illustrating the dynamic and complex interactions within our solar system, ultimately reminds us of the vast and still unknown realms in our understanding of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring our knowledge keeps pace with the ever-advancing universe.